Hi, my name is Doug Maddox. I've been working for the past 8 years on a team that develops eQuest and DOE23, and I've been involved both in the development of features for the programs and also in doing quite a bit of testing of the programs and using them for different simulation projects. And I've decided it would be helpful to share some of my experiences with using the programs and understanding of the features with the audience. So I'm going to start out with just a discussion of these sizing features of the programs. And today I'll talk a little bit about just general status of eQuest and DOE2 and the features development. And then I'm going to talk a little first from the perspective of DOE2, and for people who have used eQuest as their simulation software may not be familiar with what DOE2 is. It's actually the calculation engine that is used by eQuest. So everything that I described that applies to DOE2 is also kind of behind the scenes in the eQuest model. So I'll first talk about things from the DOE2 perspective, and then at the end I'll talk about how that translates into the eQuest interface. Here's a list of the new features in DOE2, or the key new features. There's a lot of other kind of smaller things. And I'm going to be talking today just about the improved sizing aspect of it. Next week, I'll be talking about dedicated outside air system and series chillers, boilers, towers. And then the fourth session will be just on the variable refrigerant flow. The other topics, there's quite a bit of information in the manuals, and I haven't had quite as much personal experience with those other features, so I haven't put together presentations on those yet. But I might down the road get involved with those and do some presentations. So just a status in terms of what features have not yet been implemented in DOE2.3. There are a couple of system types that are not in the program, and we don't really have plans at this point to add them. Those are the PTAC and the HVSys. There are workarounds to use other system types to model those. With the PVVT, it has to be set up as one zone per system in order to mimic the kind of system that we were previously able to do with the PTAC. As far as future updates, there's one thing that we're kind of in the midst of working on related to, there's some people have probably seen these message bomb errors where the program hits some kind of snag and just crashes. I'd like to convert all of those message bombs to warnings if possible, and not cause the program to crash, but just post warning messages and give more detail about what's going on in the program so users can resolve those things themselves instead of sending things back to me, because I can't really handle all of those. And then various specific HVAC system improvements that we'd like to try to get back into the program if possible. And we're currently looking for funding to do some of those things. So if anybody out there in the world has ideas of funding sources, I'd appreciate if you pass that information on to me, and I can pursue getting funding to get more of this work done. So let's get into the nuts and bolts of the sizing issues and features. So going back to the DOE2.2 program, talk about how sizing was handled there compared to DOE2.3. In DOE2.2, there's a load simulation that does an 8760 series of calculations to calculate loads in the building, and then passes information onto the systems program. And then the systems program uses those loads to calculate zone and coil and airflow sizing. And then it takes that information and passes it to air handler and water side equipment to calculate sizes of those. But there's not additional loops of sizing that happens, and the diversity is not really handled in the air handler and central plant calculations. So some people over the years have done a workaround for that problem where a separate simulation is done for sizing, and then peak loads are extracted from the sizing simulation, and sizing factors are applied to those peak loads, and then a secondary set of simulation is done to get the final energy results. In DOE 2.3, that secondary simulation, primary and secondary simulation is handled automatically in a single run, but it's not just a primary and secondary, it's 6 stages of simulations for sizing. So the first one is just the zone airflow, the second is air handler airflows and coils. The third stage is central plant, boilers, chillers, DHW. The fourth stage is cooling towers. The fifth stage is circulation loops, and then the final stage is some plenum extraction calculations that are done. So it's a much more involved process, but it can be done in a single step. So it does increase the simulation time, but it reduces the work involved, and it increases the accuracy of the sizing. And one thing, it can affect the length of the simulation time quite a bit more or less, depending on certain steps that you take in setting up your model, and I'll be describing those options as we go along. So when you're setting up your model, there's different ways to manage the sizing, different inputs that you can make that affect the sizing. And I've kind of categorized those into these 5 sets of inputs, and we're going to go through those one at a time. So the first is design day schedules. Design day schedules existed in DOE 2.2, but there were some expansion in DOE 2.3 with regard to weekends. So in DOE 2.2, you could only specify heating design day and cooling design day schedules that would be applied through the whole week. Whereas in DOE 2.3, there's this added feature of having different design day schedules for the weekend so that you can simulate the Monday morning startup after things are set back over an extended weekend period. So that enables you to capture this kind of higher peak loads that happen on Monday morning startup. So if you set up a model with the eQuest wizards and use default schedules that are built into eQuest, you find that there's some issues with those default schedules. For example, heating design day load schedules are typically 0. And my experience, that tends to oversize heating fairly significantly, and I'll show some examples of that further on. On the other hand, there are some code types of requirements for doing simulation-based code evaluations that specify the heating loads to be 0 in certain jurisdictions. So you may find that that's what's required, but if you're actually trying to match what designers would do or what the actual building is, you may want to look at something besides 0 heating degree day load schedules. For cooling degree day load schedules, they typically default to the same as the weekdays, which might be okay. That's at least in the ballpark of what real typical operation would be. But you may also want to define alternate design day schedules that use a higher level of operation for cooling design days. And for weekends, the design day schedules that DOE2 or that eQuest will default are going to be the same as whatever the weekday design day schedules are. So that's going to miss the Monday morning startup effects, and that's comes out the same way for load schedules and HVAC schedules. So you probably want to go in and change those from what the defaults come out as in eQuest. And my recommendation is to just always specify all 4 of the design day schedules for cooling, so cooling and heating week A and weekend. So I've got a couple of examples where I've done just kind of test simulations to show how things change with different levels of design day schedules versus normal schedules. And this is mostly all of the examples I'm going to have in this presentation are based on a small office building located in Chicago, just to kind of give a sort of a typical U.S. climate. And for this first example, I've got occupancy schedules and equipment schedules. The blue line in these is normal occupancy, so that's the schedule that would be used in the annual energy analysis. And then the red is the cooling design day schedule, and then the green is the heating design day schedule. So for cooling, the schedule is increased somewhat to value 1 from the normal annual simulation schedule, and for heating, it's bumped down just a little bit. So if we look at what that impact that has on the design day cooling and heating, the top graph is the actual hourly for the design day, the hourly cooling load, and the bottom graph is the hourly heating load. And if you do the design day calculations just using the normal schedule for your design day schedule, it's the blue line. And if you do the slightly upwardly adjusted schedule for the design days, then you get slightly higher values for cooling and heating. And so that's, you can see on the left, my comments, it's about 3% higher at the peak level, which is at the middle of the day for cooling, whoops, and at the start of the day for heating, it's about 2% higher. And those may not seem like big numbers, but as I go through this presentation, I'll show a number of different things that have kind of small to moderate effects on sizing results. But if you start compounding all those things, it becomes significant as you multiply those percentages together. So this is another example where now we're going to look at a more severe design day schedule. So occupancy, we're going to go to 120% of normal for cooling, and we're going to go to 0 for heating. Equipment, same thing, 120% for cooling, and for some reason I put 5% for heating design day. But that's not unusual for people to set those loads for the heating design day to be 0. So for cooling, much more difference now when you're comparing doing design calculations with normal schedules versus these severely adjusted schedules. So it's about a 7% shift at the peak hour. And for heating, it's 11% shift to go all the way down to basically 0 for those loads. So pretty big impact on the sizing to set those loads down or up higher or lower by that amount. So as you're doing a project, it's good to know, like, what is the designer going to be assuming when they're actually designing systems. But if you're expecting the designer to kind of design things tight, then you wouldn't want to put those more severe values in for the schedules. So the next type of input that's used for sizing is equipment sizing ratios. This is something that existed in DOE 2.2, and it functions basically the same in DOE 2.3, at least at the system level. You would set sizing ratio at if you're going like according to Appendix G, ASHRAE 90.1, where you might be wanting to oversize 15% for cooling and 25% for heating. There's this overall sizing ratio that you set to 1.15. The cool sizing ratio is how much cooling coils are sized on top of what the sizing ratio, how much additional sizing factors applied to cooling coils. So since cooling is 15%, this value of 1.0 is multiplied by 1.15 to give a 15% sizing for cooling. For heating, since the factor is 1.25, you have to calculate a value that's a ratio of 1.25 to 1.15, since it's again applied on top of this 1.15. So you would set the heat sizing ratio to 1.08696 to get a net 1.25 sizing ratio for heating coils. For the central plant, the sizing ratios that applied at system level automatically get passed on to central plant equipment. So the sizing ratios that you use at the central plant would be set to 1 generally in order to have those same 15% and 25% sizing factors. And there is now this option to have the central plant coincidentally sized. So next key input is the system sizing method. And this is a little bit of a, I would say, an awkward implementation in DOE2. It's something that existed in DOE 2.2, but it was defaulting to this value of default, the word default, for the keyword sizing method in all of the system types in DOE 2.2. So people weren't generally aware that this existed in 2.2. Now in DOE 2.3, it defaults to something else for packaged single zone systems. So I'm going to talk in a minute about what to do about that. But for multi-zone systems, it makes sense to use this default method. So what the default method means is that there's not a connection between the airflow sizing and the unit capacity, cooling capacity. And the reason that generally makes sense is that in a built-up multi-zone system, there's the ability to size the coil independently of the airflow. You can have choose to put more rows in the coil or a bigger coil or do different things with temperature set points to enable the airflow per unit capacity or CFM per ton values to be different. However, in a single zone DX system, where you're buying manufactured units off the shelf, tends to be a narrower range of possible CFM per ton, and that idea had led to this concept of a different sizing method for DX systems. So the default for DX systems, single zone DX systems in DOE 2.3 would be a sizing method of flow per capacity. My recommendation is to override that default and use sizing method equal capacity per flow. I initially just finished a fairly big project where I was doing a lot of simulations in different climate zones, and I found that particularly in cold climate zones, flow per capacity was giving me problems with unrealistic sizing. So my recommendation is to use this sizing method equal capacity per flow, and then enter a value for another keyword called max flow per capacity. And I show in a table below here kind of a pathway to getting to those max flow per capacity values. And it depends on combination of the design outside temperature and the percent outside air, because ultimately it relates to the temperature difference across the coil. And you can see that the temperature entering the coil depends on both percent outside air and outside temperature. And if you have either a high outside temperature or a high percent outside air, that's going to require a lower CFM per ton, or basically more tons of cooling per unit airflow. So this is my recommendation based on my recent experience with using the program, and I think that that's worked out pretty well for me. But as you use the program, I would suggest you maybe try this first, and if you have issues with it, I'd be curious to know, but hopefully it'll work out well for you. So the third key area of input, or the fourth key area of input, is a pair of keywords at the zone level of the program called startup heat DT and startup cool DT. These are brand new keywords in DOE23, and they're used for sizing the zone terminal. And they basically they're defined as the maximum change in temperature, zone temperature, per hour allowed during startup. So it's easiest to explain this with an example. So if you consider a zone with a thermostat set point, thermostat schedule that sets back to 55 degrees at night, and if you have this startup heat DT at 10 degrees, which is the default for most system types, then when the program is doing sizing calculations and determining the size of the equipment, it's going to be sized such that the temperature will be raised to no more than 65 degrees during that first hour. And if your actual thermostat set point is, say, 72 during that hour, then you would end up with an hour outside throttling range based on this configuration of a severe nighttime setback to 55 and a relatively lower startup heat DT. If you wanted to eliminate the hours outside throttling range problem and your set point is 72, then you'd want this heat DT to be the difference between 72 and 55, so about 17 degrees Fahrenheit instead of 10. Alternatively, maybe the owner expects the building to be a little bit cool first thing in the morning. So you would keep this at 10 degrees and just know that you're going to have some hours outside throttling range. On the other side, if you do bump this up to 17, your coils are going to be bigger, your pumps will be bigger, so there's going to be more energy use in the building because of that. There's some inefficiencies due to sizing. Okay, so the last area of input, this is kind of the bigger one that I'm going to be talking about, is the design sizing run periods and design day weather. So there's kind of two options for handling this, and the first option is using annual weather. So you do in your sizing simulations, you actually use the weather file as the basis for calculating the sizes of the equipment. And what this ends up doing is those 6 sizing simulations that I pointed out in that flow chart earlier, each one will run a full 8760 calculation process for the building through each of those 6 sizing simulations. That they may not all be applicable if your building doesn't have central plant, for example, but in any case, you're doing these multiple simulations. It's going to multiply the time of simulation by that number of sizing simulations. So it's maybe not an ideal approach in general. The advantage is that the alternative is to use design day weather. But some advantages of doing this actual weather is if your design day weather doesn't quite capture the extreme weather that's in your weather file, then you may have some issues with not meeting loads that are confusing. And if for some reason you're having trouble finding design day weather that matches your weather location, this is kind of an easy backup to that problem. Generally, I would recommend not using this approach, except maybe for debugging if you're having trouble with your design day calculations. So the next several slides, I'm going to be talking about design day weather. So design days are short design day weather periods that are defined to simulate only for a few days for like a summer design day condition and a winter design day condition. And because of that, you're doing a few years summer, a few years winter. those 6 sizing simulations don't take nearly so much time as doing 8760 weather. Is a little more consistent with conventional design process too, where when designers size equipment, they're going to typically be using design day kinds of weather conditions. And I'll talk a little bit as I go on that some of the design day weather parameters could be tweaked somewhat to fine-tune the sizing. So I'll mention some specific cases of how those might be adjusted. So in DOE 2.2, you were allowed 1 cooling design day definition and 1 heating design day definition. And that is, in DOE 2.3, that's been expanded to be up to 36 design day definitions. And the reason for that is to allow for seasonal changes and also to allow for, well, like as far as the seasonal changes, like sun angle. In the summer, the sun angle tends to be high, but the temperature tends to be high, so you get less solar gain at the peak maybe because the sun angle is high and you get more shading from shading surfaces. Whereas in the fall, you have lower outside temperature, but the low sun angle, you may have more intense solar gain in spaces. So you're able to capture that more accurately by having a different design day for summer than you'd have for fall. Similarly, schools, have, for example, might have a different building schedule in the summer than in the fall. So you have less use in the summer with a higher temperature and more use in the fall with lower outdoor temperatures. You're able to capture those differences accurately. So just for example, you might have 4 different cooling definitions, June, July, August, and September, each with a different set of temperatures and wind speeds and et cetera. And you might have 4 heating definitions, November, December, January, February. So that's a total of 8 out of the 36. So you'd probably never get up to 36, but when we just set it up, we decided to make the max that anybody would ever want to do, hopefully. Another example of where you might want more is if you have a building, say, with high ventilation rates and the enthalpy, outdoor enthalpy becomes a significant factor, you may want to create some design days with outdoor enthalpy as the primary variable instead of the typical design days use outdoor enthalpy as what they call a mean coincident variable. So it's not as intense as the outdoor temperature in those 10 days, design days. It tends to be averaged. So you might want to have somewhere the primary variable that you're maxing out is outdoor humidity, and that the dry bulb is more of the mean coincident value. Here's a sample of the DOE 2 input for a cooling design day. And I'm not going to go through everything here, but I mentioned that like some things you might want to tweak to make your design day more or less conservative. I was doing some simulations at one point and finding that I was getting some loads that weren't met. I was undersizing some equipment, and I found that it had to do with the wind speed, that I had a fairly high wind speed in as my design day. And I discovered that was actually during the design calculation, the wind was cooling off the building envelope, and I was getting higher loads during my actual annual weather calculations because the wind speed was lower for certain times when the outdoor dry bulb was quite high. So that's an example where you might put in mean coincident wind, or you might just want to set wind to 0 to make sure that you're reasonably conservative for wind. Another factor is the month and the day and the number of days. I mentioned earlier that the design day schedules now have the ability to handle weekends as different schedules than weekdays, so you can get that Monday morning startup. So in order to get that Monday morning startup, you also need to have your design day period include the weekend. So one way to be sure that that's going to happen is set it to 8 days. So you know it's going to be a whole week plus a day. So you're sure that you're going to have at least one day after the weekend. Alternatively, you can figure out what month and what day to start it at, and then maybe you could have it start on a Friday and have only 4 days here, and it would be Friday, Saturday, Sunday, Monday. So if you're wanting to minimize the computation time and the number of days of these design days, that would be a way to do that. So I'm going to talk a little bit about what the design day values need to be and where you find them and how you get them. So ASHRAE Appendix G specifies heating design day of values of 99.6% dry bulb and cooling 1% dry bulb, 1% wet bulb. And California Title 24 has heating and winter median of extremes and cooling at 0.5% dry bulb. So those are the things that are specified in standards and codes. If you look then in the ASHRAE handbook, you can see some of those numbers show up. So you've got this heating 99.6, and then here's this cooling 1%. But these are annual values of design day values. And what I've been talking about is kind of picking different values for different months. And the ASHRAE standard does have some monthly design day data available. But then, you know, there's some different values for the percentages, and it gets to be a little confusing about which ones do you pick from the monthly to match those specified values for the annual. And I'll talk a little bit about a process I used to get to that in a little bit, but these are things that you have to sort out. In general, I think the main thing is to get a reasonable design day data and to sort of be aware when you do your simulations if the sizing is coming out strange or you're not meeting loads, then it's worth maybe going back and looking at your design day data and knowing that some of the things in that data could be off or maybe not realistic. So if you decide in the end that the design day data is just not sufficient, what I did for some projects I was doing was create my own design day weather, and so I actually ran a kind of a dummy model to generate text files with all the hourly weather data, and then I imported them into a workbook and sorted them and calculated all kinds of things to get the design day weather. And I've got a few slides in here just to kind of summarize some of that logic that I went through to do that. I'm not going to go through all this detail here, but I just thought people might want to see that. But the basic concept is you sort the data and then you kind of do a ranking, percentile ranking. So that's kind of the process there. And I mentioned that there's the primary variable, which is usually the outdoor dry bulb, and then there's these kind of secondary weather variables like wind speed and clouds and humidity. And I think the ASHRAE kind of standard approach is to use a mean coincident value for those secondary variables. But I think it's worth sometimes considering that how you get that mean and whether the mean is really representative of an extreme situation, and that's going to drive the design of the building. So here I talk about kind of how the mean coincident value would be defined, and here is a spreadsheet where I've done some calculations of the mean coincident value. And again, I'm not going to go through all these calculations, but I just kind of wanted to show that the process that I went through in my project to get some of that. So I mentioned earlier that there's this issue that the standards usually specify an annual threshold for the design days. So like the 1% cooling and the 99% heating. And when you go and apply that same percentage to the monthly data, you've got a smaller set that's kind of more concentrated as hot or cold weather. And so you're going to end up with more extreme temperature. So if I go to Palmdale, California and apply this 1%, I get 104 degrees for July, whereas the annual I only get 101 degrees. And for heating, I get 25 degrees for the annual, but 21 degrees. So you're getting a more severe condition if you apply the same percentage to the monthly data. So I went through an exercise where using my spreadsheet tool, I experimented with some different percentages for the monthly to see what monthly percentage would give about the same value for that month as the annual value that I got from that weather set. So 5% for these particular cases seemed to be about equivalent, and on the heating side, 97% was pretty close to equivalent. So that's just something that people should be aware of if they're going to be doing any kind of processing of their own weather data, or even if they're looking up data in the table. If the code says 1%, maybe when you're looking at monthly, you should be looking at more like 5%. But again, I wouldn't stress too much about it if you're getting reasonable sizing results from your model, and over time and experience, you'll be able to compare the sizing you get from the model to sizes that actual designers are coming up with, and you can kind of fine-tune your approach to doing these things. But it's good to just kind of have a better general understanding of how it all works and where you might go with it. So I did some additional simulation experiments with weather and other design. These aren't just weather, other kind of building design features, just to show how different things will affect the sizing. So I'm going to start out with this heating dryball range. So when you look at the ASHRAE published design day data, usually they don't specify a range for the outdoor temperature on the heating design day. They'll specify it for a cooling design day, but not a heating design day. So what I mean by the range, it's how much it varies from the extreme case to the less extreme case on that day. So for heating, in this case, I think this is probably Chicago. The heating design day was in the file was -8 degrees, and so I'm doing two different simulations. One with that held flat, so I'm setting the range to 0, and the other I'm setting the range based on what I found in the weather file, which causes it to go from -8 to +15. So the range is about 22 degrees. So the entry into DOE23 would be 22 degrees for the daily range. So the result of that difference is shown down below. So the design day heating, this is a 24-hour load profile for that building. And when the system comes on in the morning, you get that peak. And with the daily range, you're getting significantly about 5.6% lower peak than with a flat profile. This particular case has the fan cycling on at night, so it's maintaining some kind of a setback temperature at night. I ran the same building without night cycling, so the space can get pretty cold at night. And in that case, it was about 13% higher peak with the flat outside air temperature. So that's just an example of a case where coming up with your own design day weather, you're able to define this daily range, whereas if you're limited to the weather in the ASHRAE, you're not going to know that daily range. So a couple more examples of things that I tested. I kind of put these examples together based on a couple of years I spent using the program, the design sizing features, and different problems I ran into. So I'm just kind of explaining, to avoid those pitfalls that I hit. So this is a case where you're including the weekend or not including the weekend in the design day period. So in the red case, the design day period might be Monday through Friday. So you're only getting weekdays in that design day period. In the blue case, you're getting the weekend. So this design day is probably a Monday, and the system's been down in a night mode all weekend, and suddenly the building's a little bit colder than it otherwise would be, and you get a fairly big peak, or hotter, I guess, in the case of cooling. The top one is cooling, I'm sorry. And the bottom one is heating, so you get bigger peak loads for both cooling and heating when you include that weekend. And it's a pretty big difference. It's 10% for this model for cooling and 9% for heating. So, that just kind of shows that it's really pretty important to include the weekend when you set up your design days. Some other issues that I ran into were related to thermal mass. So I've got actually kind of two different approaches to looking at that problem. The first is with furniture weight keyword in the model, and I'm comparing a furniture weight of 16 pounds per square foot to 2 pounds per square foot. And so again, the top graph is cooling, the bottom graph is heating. And with the higher thermal mass, you have more heat energy being kind of stored into the mass during the nighttime period. So in the morning startup, it takes a larger amount of energy to either cool or heat the building because of that mass of the building it has to heat up or cool down. And it's 8% for cooling, 15% for heating. So these are pretty big numbers, impacts on the sizing. I also did a test with interior wall type and comparing an air wall to a light frame wall, just to kind of give an example. You might do a similar test with a light frame wall versus a concrete wall. But the idea is, again, that the thermal mass is going to kind of cause the stored energy that has to be overcome by morning startup to be greater. So having more thermal mass in the model requires a greater amount of energy at startup. So here's a couple of points about HVAC controls and what goes on with those during the sizing parts of the simulation. Outside air economizers are active during sizing by default. And in the work that I've done in the past, there have been some cases where economizer has kind of fouled up the sizing calculations. So we've, in our models, we deactivated economizers, and you can do that in DOE23 using this system keyword called econo schedule. And it's an on-off type, and you just set it to the value to 0 during all of the design day types. So there's the design day period that has a value of 0, and otherwise it has a value of 1 just to enable economizer operation. Similarly, supply air temperature control, some things are active and some things are not active during sizing. So if your model has a reset control, that would be active. Warmness control is not active. I'm not really sure why things were developed that way, but that's the way it is. So I'm just kind of laying it out there for people to be aware of. And that kind of generally is not going to affect sizing much, but because during the peak periods, the reset controls are usually not really doing very much. Similar for central plant, the load reset control is active during sizing. So I've got a couple of slides about once you've got your sizing model running, how do you go about checking to make sure the sizing results are reasonable? You can look at actual sizing values in the SVA, and there's a new report called SVC. And then in the plant equipment PSH reports, I'll show some images of those in a few slides down. And then I think it's really helpful to look at scatter plots of the hours in each part load range that are available in the SSP and the PSH reports. So I've got some of those to look at here. So if you've got at least a few hours in kind of the upper ranges of part load, generally that's what you expect to see. You may, for some reason, expect things to be oversized more than that, but it's good to at least check these graphs or charts to make sure that things are the way you expect. If you see a lot of hours in 0 to 20, then that's probably a sign that their sizing went wrong. Similar for, this is a chilled water loop in the central plant, the PSH report. So the next topic I'm going to cover is sizing data transfer and also just sizing data entry into the models. But as far as the data transfer, this is kind of applicable when you're looking at an existing building model where measures are getting applied to existing building and some of the HVAC equipment is not getting replaced. So you have, and maybe you don't know all of the sizes of the existing HVAC equipment. So maybe you're going to auto size some or all of that. So in that case, you would want to do the sizing in the base case model and then be able to transfer key values from the base case model that was auto sized into the measure model. And even if all the sizing parameters are known, you still need to be careful to enter the same values and key inputs to both the baseline and measure. And I'm going to talk a little bit about what those values and inputs are for a couple of examples. So the first example is a DX air handling unit, and the values that if you're trying to transfer sizing from a baseline to a measure, that you would want to capture all of these values from system and zone. And then there's some additional values that are important to have consistent. For example, cooling capacity specified on a cut sheet is going to correspond to some entering dry bulb temperature, entering wet bulb temperature, and entering condenser temperature. And if it's different from the AHRI standard, you would need to enter those values into these keywords down here. Similar for if you have a heating system, like a heat pump system, there's similar keywords for those. Once you've done the simulation, this new SVC report that I mentioned earlier will have the sizing results in it. And this table is fairly complicated, and it's good to kind of understand what's going on here. There's 3 kind of sizing related rows in this that you'll see repeated. The first is what's called the design day peak. So that's actually the calculation of load based on the design day weather conditions. So you'll see the design day weather conditions and the time that it happened, and then the airflows and other parameters that were determined by the program for that. And then there's, in some cases, the program may manipulate values based on certain parameters in the input. For example, the capacity, the sizing method that I talked about earlier, where you have CFM per ton. If you have a CFM per ton listed, it might adjust the CFM like it did here relative to what was in the design day calculation. So it actually forces the CFM to be a little bit lower than what the design day calculation. So that's your design condition. And the design condition has certain airside temperatures that are not AHRI. So this last row is going to the rated conditions. So you've got the AHRI 80, 67, 95 values, and it adjusts capacity and these other factors based on the AHRI conditions. So 3 different kind of design related things going on there. This is similar kinds of information for a chiller, and I'm not going to go through the details here, but you can go back and read this on your own. And similar output in the PSH report where there's the AHRI numbers and design numbers that come out for chillers. I see a question popping up. I'm just going to wait until the end. We're getting close to the end. I'm going to kind of whip through the last of these, and I'll take a few minutes for the questions. So again, if the sizing is known, it's important to be consistent with keyword value. So if you have a rated value for capacity, make sure you get the right temperatures and flow rates that correspond to that. And always check results to make sure that what you're getting out of it makes sense. So I've got a few slides that I'm just going to breeze through related to the eQuest interface. And again, I'm going to post this so people can go back and look at it. But here's the design day sizing stuff or schedules, and you can see the defaults in green are not always what you might want, and I've changed some of those in red on the right to be something that makes more sense to me. Here's how the interface for entering design day values for the design day weather. System sizing related values are identified here, kind of general information, cooling related information, and heating related information, and zone cooling related information. And this is my last slide. If I went through that kind of fast, and again, I'm gonna post this stuff where people can get to it. I'll put links on my web page to get to it, maddoxenergy.com. So it might take me a couple of days to get that all up there. But one thing is there's this file that's available in the eQuest release called bdldialogues.txt. You can search for the DOE23 keyword to figure out, if you can't find it in the interface, you can kind of follow this process looking through that file to find what tab it's in and what sub-tab. And if you're going through that process, you need to make sure you're looking at the correct components. For example, some keywords apply to both zone and system, so you need to make sure you're following the logic for the correct one. So that's all I have for slides. I'll be resuming the next presentation next week at the same time, and also 8:00 a.m. East Coast US time as well. Thanks for coming. Goodbye.